Okay, so in example number one, what we're going to do first is we're going to draw an extended force diagram of the problem at hand. So of the pulley itself, we have the earth pulling on the pulley at the center of mass. So I'm going to draw the force of the earth exerted straight down. We also have pulling down the force exerted by the string and the hanging mass, all right, which I'm just going to abbreviate as F of the block. And then at the pivot pointing up is going to be the force exerted by the pivot, or the hinge, or the axis of rotation, whatever you want to call it. I've labeled clearly both radii, and just like a force problem, you would set this up um, with your extended force diagram, and then instead of using Newton's second law, if we look at this, the force of the pivot and the earth are exerted at our axis of rotation, so they're not going to cause it to rotate. So the only force that is going to give this a torque is going to be the force exerted by the block. So that is exerted a radial distance of 0.3 away. So we have the net torque divided by the inertia of the object is equal to the angular acceleration. Setting up these problems are very similar to setting up Newton's second law problems, except you are just concerned with the torques and the forces that make this object rotate, and when they rotate, they accelerate, and that's called an angular acceleration, that alpha there. So in order to solve this, we then have 1.2 newtons times 0.3 meters divided by the inertia, which is 0.4 kg squared. I had listed all the givens straight up in the problem, so you didn't have to worry about, reading through the problem in this video. When you guys solve for the angular acceleration, you get radians per second squared. We'll discuss more what a radian is next week. Now, the way you can kind of view this is very similar to setting up Newton's second law. You have the sum of the torques over the mass is equal to the acceleration. So you're setting up the analogous rotational parts. Torque over moment of inertia, or rotational inertia, is equal to angular acceleration. So that would be draw an extended force diagram. As this occurs, this pulley will slowly gain angular velocity. So the acceleration is increasing. Or sorry, the velocity is increasing and the acceleration is staying constant. All right, so to determine the angular speed after 4 seconds, your angular motion equations are very similar to your linear motion equations, except we just use different symbols. So it's our angular speed equals our initial angular speed plus our angular acceleration times time. Just like we would do with our regular velocity equation, we do the same thing with the angular information. So our initial angular speed is 0. Our acceleration is 0.9 radians per second squared. And our final angular speed, we don't know. We know the time is 4 seconds. We can use the same expression we would for linear motion, but with its angular counterparts. So our initial angular speed, which is 0 times the acceleration times 4 seconds, will give us 3.6 radians per second. And then, very similar to graphing, we know that the initial angular speed increases as time goes on at a constant rate. And then our angular acceleration is going to be constant the whole time. So our graphs would look, for velocity, a diagonal line; for acceleration, a horizontal line at 0.9 radians per second squared.